Colleagues, today I would like to present you my presentation named Acoustic, Magnetic, and Structural Characteristics of Cyclic Degradation of Traditional and Additively Manufactured Steel. In this work, we investigate two types of materials, and it will be two part of this presentation. The first material is additively manufactured 316 steel. In this slide, you can see microstructure of this steel with some austenitic grains, melt pool boundaries, some pores, and lake of fusions. This material was obtained from a powder composition of 2463 micrometers using selective laser melting. The second material is traditional rolling stainless steel with three types of grains. Grain size is 21, 117, and 218 micrometers. In this slide, you can see the table with mass fraction of elements and the mechanical properties of our materials. This is a specimen thickness 0.5 millimeters, and in this area was assessed some parameters. In this study, we use tension with loading rate 0.5 millimeters per minute. Fatigue tests two different values of number of preload cycles, and after the fatigue, we make a static loading tension, and we call it cyclic degradation. Damage assessment was use optical microscopy. I will tell about it in the next slide. And we use some parameters of non-destructive testing. For example, ultrasonic velocity, eddy current, digital image correlation with quantitative estimation of weak and high area of strain, and acoustic emission. To assess damage, we use special methodology. First of all, we take some pictures during the tension of our specimen after cyclic degradation. We use a special program for process our damage patterns. It include taking the original image, the process of binarization, and the process of identification of defects and some structural elements. After the identification of defects, we calculate some characteristics, for example, number, length, area, frame area, defects, inclination angle, and some the relative deformation. It's a characteristic of our static test. After the identification of damage characteristics, we calculate some damage criteria. For example, defect density, average length of defects, relative area of damaged surface, and some other. In this work, we will speak about the defect density, the relative area of damaged surface, and about the exponent in cumulative distribution of microcracks. The first part is an experiment with additively manufactured 316 steel. In this experiment, we provide damage assessment after cyclic degradation to relative durability 0.3 and 0.7. And after the cyclic, we start to tensile to static loading our specimen. First of all, I would like to show you the results of cyclic tests. Here you can see our curve, fatigue curve for our material, and some literature data. Our material is not very good, but the reason is that we don't have any heat treatment. We only print these specimens and start to investigate them. And after we start to fatigue tests for our specimen, we looked at many small fatigue cracks on the polished surface. And here you can see one of them, it's this fatigue crack nucleate and start to growing through the melting pool boundaries. This is the reason of worse fatigue properties of this investigated material. But we understand that if we make some heat treatment, we can get a better result of fatigue properties. After the cyclic degradation, we make a tensile test. Here you can see the results of damage assessment in the of spaceman in the initial state. We can see one horizontal crack which nucleate horizontally because of the melting pool boundaries. After the cyclic degradation, after the cyclic test and tensile, we see not only one crack, but many, and they start to nucleate, coalescence, and grow through the melting pool boundaries. It's the biggest problem of this material. And after the big number of pre-cycle durability, we can see one big microcrack with the biggest opening of it, and the fracture was provided through this crack. In this slide, we can see the quantitative results of our damage assessment. You can see the curve of relative damaged surface area and the curves of density of surface defects. We can see that the biggest number of relative damaged surface area we find in the material without any cyclic tests. But after we start to make a tension, you can see the increase and decrease in the density of surface defects curves. It connects with the coalescence of microcrack in the third stage of tension. We don't see it in the material after big number of cycles, and we see the coalescence in the final stage of fracture in the material with 0.3 relative durability. With damage assess, we try to find a correlation of non-destructive testing parameters and damage area, relative damage area. Here you can see the results of eddy current and ultrasonic velocity of our material during tests. And we find that every curves OB to power law relationship. The second experiment was provided with stainless steel with three types of grains size 27, 117, and 218 micrometers. First of all, here you can see the results of UBSD analysis provided by our Indian colleagues. You can see the microstructure of material in the initial state and in the state after tension. We find many martensite in the biggest number of martensite. We can see in the material after tension with 218 micrometers grains size. Here you can see the same deformation dependencies of two parameters, relative area and the density of microcracks. We find that the biggest damaged relative surface we can see in the material with the biggest grain size. But we see that microcrack coalescence on the second stage of tension we can see only in the material with the lowest grain size. Here you can see the results of digital image correlation. I would like to say that we make not only that we make a quantitative digital image correlation with provide with estimation of area of the weakly deformated plastic zone and the area of the highly deformated plastic zone. We find that in the state with grain size 21 micrometers, we have rupture, but when we rupture fracture, but after heat treatment to 218 micrometers, we have shear rupture, and we see it in the digital image correlation pictures and in this curve because of highly deformated plastic zones start to grow in the third stage of fracture. And also we find that the area of weakly deformated plastic zone orbit to hole patch to the equation similar to hole patch equation with a square of grain sizes. The last one is results of acoustic emission. We make some tests with acoustic emission identify and its famous parameter of B value, which firstly was created in seismology by Gutenberg Richter, and nowadays we have many investigation which used B value parameter. And in this work, we try to estimate B value parameter by acoustic emission here and by damage cumulative curves by the similar equation. And we get some result. Here you can see the curves of B value using acoustic emission and using damage. In third and fourth stage, it's the same, but we have some not the same results in the second stage. Well, in this work, we quantitatively evaluated damage criteria using binarization, find the effect of cyclic degradation on our material additive steel. We find that non-destructive testing and the damage area are related by a power relationship. And we find that quantitative DIC parameters for steel OBI an equation similar to the hole patch, and we try to estimate B value parameter using acoustic emission and damage assessment method. So I would like to say that the main conclusion is that the set of methods used for analyzing the destruction process allow us to evaluate the criteria for material degradation at different stages of loading and establish the relationship with the characteristics of non-destructive testing. It's a practical question. Thank you for your attention.